Okay, so first, have you received my email message about our TA?
Yes.
Yes, right. So the dissertation will start tomorrow, every Wednesday, right? From 6:30 to 7:35. Okay. So his name is what? Joseph Cruz,
Yeah.
right? So he will be here tomorrow. What? His name, you just look at my email message. I sent you email message this afternoon about the dissertation.
Yeah, we basically
right?
the same time.
And the same time, yeah. Yeah, same format, the Zoom meeting, okay? The Zoom meeting. But it's not me. He will come here, right? He will come here and he will conduct the dissertation tomorrow, every Wednesday, right? Tomorrow is Wednesday, right? So every Wednesday, he will do the dissertation. And please ask him about any homework problems you have, okay? You say, oh, I cannot do this problem, please solve that for me, and he will solve it for you, right? And in the last 20 minutes, he will give you the quiz, okay? So remember, you have to use your own papers for the quiz, right? You have to write down your name and your student ID number on the upper right corner of the paper, right? And then after you complete your quiz, you have to what? You have to send your work, not to me, but to him, to Joseph, okay? You can send by email, for example, right? You can send to him, okay? You have to what? You have to scan your paper, right? And send your work to, not to me, okay? To him, to Joseph, okay? And tomorrow, don't forget that, okay? If you send me, there will be no point because he will what? He will grade the quiz papers, not me, okay? So you got to remember, you have to send your complete finish after you finish the quiz, right? You got to send you got to scan your paper, right? And then send the paper, send the scan, right, to him, okay, to him. That's the quiz for tomorrow. Any question about that? Please ask. If you have any question, if yes.
Do we just take pictures of them and send them to him? Yeah. Okay.
I think it's much better. It's much better for you to scan. If you take a picture, very likely the picture will not be very clear, right? It happened in the spring. Some people send a picture to me, right? But the quality is not very high. Okay, it's very hard to read. It's better for you to scan, right? Okay. I think your phone has some scanning function. Yes or no? Can you scan by your phone? Yeah, so you do that, okay? Don't take a picture because take a picture is not very clear. The image is not very clear. Sometimes it's very, it's very vague. It's not very clear, right? So I think it's much better for you to scan, okay? By using so-called the PDF format, right? That's much better, okay? Any questions so far? You can ask because there'll be the quiz for tomorrow, right? So the quiz for tomorrow will cover only for chapter 1, okay? Chapter 1. Nothing about chapter 2 will be on the quiz tomorrow, okay? So the quiz for tomorrow is only for chapter 1, okay? For chapter 1. So this is easier. Why? Because everything from chapter 1 has been covered up before, right? There's nothing new here, right? Nothing new here. So you don't have to worry about too much, right? You don't have to worry about too much because everything is new, okay? Nothing new, okay? Nothing new. Everything is quite standard, right? Quite standard. Any questions so far? That's the format for tomorrow's quiz. Also, you have to show your work, okay? If you no work, no what? No credit. Remember that, okay? No work, no credit. If you just write down the answer, nobody knows. How can you arrive at your answer, right? So remember, okay? No work, no credit. You got to show your work in order to justify your final answer, right? That's the important part. But otherwise, you get 0 point. Even though your answer is the right answer, if you have no work to support your answer, you get 0 point. Okay? All right. So much for the quiz tomorrow. So remember, we have a quiz every Wednesday now, right? Every Wednesday. And Joseph Cruz will come here. Okay. So tomorrow he will be here, right? He will conduct. He will be the host for the meeting, right? For a meeting. Okay. And a question. And a question. So Monday, Tuesday, and Thursday, I will be the host, right? But every Wednesday, he will be the host. Okay. Joseph Cruz will be the host for the Zoom meeting, right? For the Zoom meeting. And a question. Okay, let's continue with the chapter 1. Okay, so we're almost finished, right? So let's continue with that. Okay, continue with that. Let's continue with the, no, that's not what I want. I want thinking. Okay, I want the ebook. Okay, I want the ebook. So let me, ebooks. So far, the weather has been fine, right? I hope the weather will be fine tomorrow. Who knows? It's hard to say right now because the.
What will we do? What will we do if the weather? What will we do if the weather turns?
It's hard to say. Let's. If the power is down, then we cannot do this anymore, right? Let's wait until tomorrow to see what happens. Okay. It's very hard to say what can we do now, okay? Well, what we can do right now. Because everything is up in the air, right? So it's very hard to say. Okay, let me open the ebook for you, okay? Please wait for a few minutes. Okay. Let me, okay, I want to share the screen with you, okay? So this is the share screen, right? I want to share screen with you. So you can see that. And which one I want to share? So, okay, here, right. Okay, that's it. Okay, this is the thing I want to share with you, okay? This is the, let me enlarge that so you can see very clearly, okay? Very clearly. Okay, you can see very clearly. Okay, now let's look at we have discussed the combination of functions, right? Today is Tuesday, so Monday we have to discuss combination of functions, right? Sums, difference, products, quotients, that's easy, right? You can add, you can subtract, you can multiply, you can divide two functions, right? That's easy. Now, one thing is, I ask you to remember is what? Composite functions, right? So let me, okay, composite functions. You see the composite function, okay? Okay, it's called composition, okay? Composition. So you got to remember, let me just, okay, composition of function. Okay, this is the composition of two functions with f, see here, right? This is the composition of function. Y to fu, right? U is another function of gx, right? So you compose f with g, right? You compose f and g, right? So it's called, the new function is composed of two given functions, f and g, right? So the new function is the composition of f and g. Okay, there's a new operation, right? F is a function, and G is a function. Now you combine them, right, to get a new function. So new functions are formed from two old functions, right? Not through addition or so on and so forth, through so-called composition, okay? So this is so-called composition. This is notation, see? F circle Y. G, right? So please remember, okay? What's the meaning for F circle G, right? So F circle G is a new function, right? F circle G is a new function. So what does that mean? This new function, right? So please write down, okay? F circle Gx equal to what? Equal to F of what? Gx. That's the definition of the circle notation. Okay? Gx. So please write down, okay? F circle, small circle. This is small circle, okay? Small circle. Okay, F small circle G is a new function, right? This is X, okay? This is X. Is equal to what? F of Gx. Okay, that's the definition of this. Okay, small circle, F circle Gx equal to F Gx, right? So this is standard, right? Now, okay. Just want to clear, okay. Okay, let me just share the screen with you, okay? Okay, now let's look at further, okay? Look at further here. See, right? As I said a few minutes ago, right? F circle Gx equal to F of Gx, it's right here, right? So this is what? The composite function of F and G. This function will be very important in the future, okay? In calculus, we have to use composite function many times, okay? The composite function will be very useful in the future, okay? So this is a new operation, right? Take a look at the video if you want, okay? Video. Okay, see.
To show you the value of the composition of functions, we're going to figure out the model for a basic occurrence in nature.
Something wrong with here, okay.
The ripples in the water are larger and larger circles created over time.
Very slow, I don't know why.
If we know the rate at which the ripple in the water travels outward, what is the model for the area of these circles?
Okay, let's don't watch that. It's too slow.
With respect to time. Here we use a composite of two functions to get the answer. A stone is dropped in a pond, creating a...
Do you want to watch it?
circular ripple that travels outward at a speed of 50 centimeters per second. A, find the function g that models the radius as a function of time. B, find a function f that models the area of the circle as a function of the radius. C, find f of g. What does the function represent? Part A, the radius is increasing at a rate of 50 centimeters per second, and the distance is equal to the rate times time. So we have the radius is equal to 50t. G of t is equal to 50t. Part B, the area of a circle is pi r squared, so f is equal to pi r squared. C, f of g is equal to f of g of t, which is equal to pi times 50t all squared, which is equal to 2500 pi t squared. This gives us the model for the area of the circle created by the ripple with respect to time t.
Okay, very good. Okay, this is so-called a composite function. You have two functions, right? F and g. Now you want to compose it to get a new function, right? F is pi r squared and the gt is 50t, right? You compose it, become what? Pi 50t squared, right? It becomes 25 100 pi t squared, right? So it's a composite function. So it becomes a function of t, right? Function of t. Okay, very good. So we have done this part. Remember, f and g and gf are not same, right? You got to remember, in general, they are not same. Okay, so I told you this yesterday, right? See, this is very important for you to understand, okay? Please circle these, okay? In general, f circle g and then g circle f are not same. Okay, so look at that, right? Look at this. F circle gx is x minus 3 squared, and then g circle fx equal to x squared minus 3. They're not same, right? They're not same. X minus 3 squared, if you expand, right? This is what? If you expand, it will be what? X squared minus 6x plus 9, right? Plus 9. Okay, if you expand x minus 3 squared, you have x squared minus 6x plus 9. This is x squared minus 3. Apparently, they are not same, right? So in general, these are not same. You got to remember, okay? F circle G and G circle F are not same in general, right? Of course, in special cases, they may be same, right? But in general, they are not same, okay? They are not same. Be careful. You have to know the order important, right? Fg and the Gf are not same, right? But everybody knows that F plus G is equal to what? G what? Plus F, right? For addition of two functions, you can switch the order, right? Also, for what? F times G, right? Is equal to what? G times what? F, right? For the product of two functions, the order is not important, right? Just like what? 5 times 2 equal to 2 times 5. They are both equal to 10, right? So for the product of two functions, the order is not important. For the sum of two functions, the order is not important, right? But for the composite functions, order matters here, right? Fg and Gf, F circle G and G circle F are not same in general, right? So remember, for the product, order not important. For the sum, order not important. But for the composition, order does matter. Okay, order is important. All right, you got to remember this. Okay, this is a key point in this section. Okay, you got to remember. Okay, you got to remember. Okay, got to remember. Now let's continue with. We have done this actually, right? Now you have to know how to composite, right? This is example 7. You got to know how to composite Fg and G circle F and F circle F and the G circle G, right? Now let's do this. Let's do part C, okay? Let's do part C. Without looking at the answer, right? Let's do part C, okay? Part C. How to do part C? Let's try part C, okay? Part C is what? F circle, right? F. Now you want to what? Find this function, right? At x, right? At x. Now you want to evaluate this function, right? So first write down the definition, right? What does it mean? F circle F of x, right? This is nothing of f of what? Of fx, right? Fx. That's the meaning for this, right? F of fx. So what's fx? Right? Fx is square root x, right? So you have what? You have f is outside, right? Inside is square root x because fx is defined by square root x, right? So this is f square root x. Okay, so now you have to ask yourself, what's f square root x mean? Fx is square root x, so you have to replace x by square root x in order to get f square root x, right? So this is equal to, so remember fx is square root x, so you have to replace x by square root x, right? To evaluate this function, right? You have what? Square root x. right? This square root is definition, and inside the variable is square root x, right? Square root x. Now what's this? Tell me how to simplify this. You have square root, and you have square root, it becomes what? The fourth root, right? The fourth root. Right? Or you can write this as a power form, right? This is x to the power what? Tell me. What's the fourth root? What's the power form for fourth root?
Quarter.
William? Yeah, 1/4, right? 1/4. So we have found the answer, right? You can either use this answer or you can use this answer, right? So the answer is what? Is the fourth root of x, or x to the power 1/4, okay? For f, circle f of x. Okay, so everybody should learn how to handle these, okay? How to handle the composite of two functions, right? So this is very important in calculus, okay? You got to remember how to do the composition of two functions. So we have found the answer for C, right? So the answer is fourth root of x, or x to the power 1/4, okay? So that's, okay? Yes, that, because you can, okay, sorry, but don't worry, you can see the answer right here, see? For C, right? See here, right? F, circle fx is fx, f of square root x is square root x, right? The fourth root of x. Okay, the fourth root. What domain for this? What domain for this? For fourth root, right? X cannot be what? X cannot be a negative number, but fourth root, right? Fourth root. So you have or 0 close interval to positive infinity, right? To positive infinity. So you can find domain for any functions, right? The domain is this, right? It's the close interval 0 to positive infinity, right? So this is the answer for C. And I told you is fourth root of x, right? Fourth root of x. All right, this is straightforward, right? Now you can do what? You can do more than 2, right? F circle G circle H is what? F of G and HX, right? You can do more than 2. You can do 5. You can do 7. So, right? The definition is similar. Okay. So I don't want to spend too much time on these, right? See, F circle G circle H is F over GH. You do it one by one. First, you put HX inside, then do G of HX, then finally go from inside to outside, right? You get the answer like this. Okay. Okay. You can also do what? You can also do. You can also what? You can also do going what? You can also go backwards, right? This is a composite function, how to decompose f of fgh, right? Just going backwards. See how to, let me show you how to decompose, right? Decompose. Okay, how to decompose. Just going backwards, right? See, this is a function which is given, right? Is cosine square x plus 9. You have to find what? Functions f, g, and h, such that capital F is f circle g circle h, right? So it's easier to decompose, right? We learned how to compose, right? Now you have to what? Go backwards, right? You know the composite function, you want to find their components, right? So first write this as this, okay? Because cosine square x plus 9 is the same as cosine x plus 9 square, right? Now look at that. The formula for f says that you first what? You first add 9, right? Then take the cosine function and then take what? The square function, right? See, first add 9 first. You add 9, then you take what? The cosine of the function, and finally you have what? You have square, right? So you can have this, right? Hx is first, right? X plus 9. The middle part is what? cosine, right? And the outside part is square, right? You can do it, see, right? You can do it, right? See, right? So you can finally, you can get the capital Fx, right? So this is the F, this is the G, and this is H. Okay, so you can do decompose, right? You can do the composition of functions, and then you have a compose the function. You can what? You can decompose into F, G, and H. Okay, that's straightforward. You're going backwards, right? You're going backwards. Okay, you're going backwards. So that's easy. Now we have finished. Okay, we have finished. Nothing new is here, right? So let's go to next page. This is what? This is just exercise, right? Yeah, it's just exercise. Okay, nothing new. Now we have finished section 1.3, right? And 1.4 is very easy. Okay, 1.4 is very easy. What's 1.4? Exponential functions, right? Actually, we have discussed this yesterday, right? How to deal with exponential functions. This is definition, remember? This is definition, fx equal to b2x. We have discussed this yesterday, remember? So this section is nothing new, right? b2x, okay? B is a positive constant. So remember, B is a positive constant, okay? So that's the so-called exponential function. Now, I want you to refresh your memory. How about this function? If I have this function, what's the name for this function? Gx is equal to x to power a. What's the name for this function? Remember?
Power function.
Power function?
Are they same? What?
No.
What's the name for this function? This is exponential function. But what's the name for this function? We have discussed this yesterday. What's the name?
Power function.
The special name associated with
Power function.
Right.
Power
Please
function.
remember, okay? This is so-called power function. Power, P-O-W, P-O-W-E-R, okay? Power function. Okay? Don't forget that, okay? Exponential function and a power function are not sign, right? Why not sign? Because exponential function, b is constant, right? Here, for the power function, the exponent is constant, right? Let me give you an example here. Fx is equal to 6 to power x. This is what function? Exponential function, right? But gx is equal to x to power 6. What's the name for this function? Power function, right? They are not sign, okay? 6 to power x is exponential function. X to power 6 is what? Power function. All right, so they look quite similar, but they are not totally different, right? They are totally different. Okay, now there are a lot of exponential functions, right? So you say 9 to x, right? You have what? 1/2 to the power x, right? So you have a lot of what? You have a lot of exponential functions. Of course, you have a lot of power functions, right? See, x to power what? 9 and x to power 1/2, right? You have a lot of what? You have a lot of power functions, you have a lot of exponential functions, right? But they are not sign, they are totally different, okay? So don't get confused. Power function and exponential function, they behave very differently, right? You got to remember, power function and exponential function, they are very wide apart, okay? Wide apart. They are not similar at all, right? Even though they look quite same, right? But their behavior is very different. Okay, it's very different. Now let's continue. Okay, let's see what's new here. I don't think there's anything new here, right? Now this is the meaning for power, right? Of exponential. Now this is a picture, right? For y equal to 2 to x, right? This is a picture, okay? We have discussed yesterday, right? It's what? It's an increasing function because this 2 is larger than 1, right? It's an increasing function. And this is what? This is so-called the vertical, no, the horizontal asymptote is x-axis, right? Because this curve and this line cannot what? Cannot touch, but they can go very close, closer, but not touch, right? Not touch. So this is called what? Horizontal asymptote, right? So we have discussed this yesterday, actually, right? So it's nothing new here, right? Now you can what? You can approximate, right? This is a picture for 2 to x, for any x, for any real number, right? 2 to the power 0 is always equal to 1, right? So got to remember, right? For anything, right? Right? Actually for any b, right? B to the power 0 is always equal to 1, right? See, at x equal to 0, the y value is always 1 for the exponential function, right? So the curve will always pass through 0, 1, right? Increasing, right? Increasing, you can go up forever. And this is what? This is horizontal asymptote, right? This curve and this line can get closer, very close, infinitely close to each other, but not touch, right? So this is so-called what? Horizontal asymptote, right? Horizontal asymptote. Okay, horizontal asymptote. This y to 0 or x-axis, right? Horizontal asymptote. Okay, so remember the shape for exponential function. Here is b is what? B is larger than 1, right? So b is 2 here, right? B is larger than 1. If b is smaller than 1, then the curve will be different, will be decreasing. Remember? We have discussed this yesterday. Right? So this is the picture. Okay? Now look at this, right? As I told you, right? This is a picture for exponential functions. Okay? Exponential function. Look at picture, right? Tell me what's this point? Tell me what's this point? They'll pass through this point, but what's this point? What's this number here?
1.
What's this number here?
1.
That's
1,
number
right?
1.
The number is 1. Yes, 1, right? It's 1, okay? Because at x equal to 0, for any exponential function, it's always equal to 1, right? So remember, this number is 1, okay? The number is 1. Don't forget that, okay? Now you can see that this is what? 2 to x, right? And this is 4 to x, right? And this is what? 10 to x, right? If this number gets a lot larger, the curve gets what? Gets infinity fast, very fast, right? Very fast. So they are all what? They are all increasing, right? They are all increasing. Now, if b is less than 1, see, this is 1/2, right? This is 1/4. The curve becomes what? Decreasing, right? Decreasing, right? Decreasing. Not increasing anymore, but decreasing, right? See, 1/2 is less than 1. 1/4 is less than 1, right? The curve becomes decreasing, right? But you got to remember, either increasing or decreasing, the x-axis is always what? The horizontal asymptote, right? So this is always horizontal asymptote. Okay, horizontal asymptote. Okay, so this x-axis is always the horizontal asymptote, no matter b is positive, no matter b is larger than 1 or smaller than 1, right? This is always horizontal asymptote. So this is a special point, okay? 0, 1, right? This is a special point. Don't forget that, okay? The point is special, right? Because any exponential function will always pass through this point, 0, 1, okay? Okay, very nice. This is so standard, right? So standard. Now let's continue with something new. Let's see, does it have anything new here? Look at that, right? This is y equal to b to x, b is smaller than 1, right? It's decreasing. If b equal to 1, it becomes a constant function, right? B larger than 1 becomes what? Increasing function, but we always pass through this point, right? 0, 1, and you see 0, 1, right? So no matter b is less than 1 or b larger than 1, the curve always pass through this special point, 0, 1, and 0, 1, right? Let it go. Okay. Okay, now this is loss. Okay, so please remember these laws. Okay, we have learned this. Right? We have learned this. They called what? Law of what? Laws of exponents. Okay, so you have how many laws? 4 laws, right? 4 laws. Don't forget. Okay, you have 4 laws here, right? Bx times b to y, you can add is bx plus y, and the bx over by, you have to subtract the exponents, right? So it's bx minus y. And bx to the power y is bxy, and abx is ax times b to x, right? You got to remember, okay? But that's wrong, okay? Don't make this mistake. How about this? Somebody say, can I have this? Right or wrong? Ax plus ay is equal to ax plus y. Right or wrong?
Wrong.
Do we have this? Wrong. Why is wrong? It's wrong. It's a terrible mistake. What's the right formula? The right formula is this. Okay? By using the first law, right? Ax times ay. Right? Then you can what? You can add the exponent, right? It's ax plus y. That's right. This is right, this is wrong. Okay, don't make any mistake. This is ax times multiply, right? Times, okay? Times. Okay, ax times ay is ax plus y. We don't have any laws for these. We don't have any law for x plus ay. We don't have any law, any formula for the first one. This is wrong, right? But this is the right formula. This is from the first one, right? So this is right. Okay, so for example, 3 to the power 5th times 3 to the power 95. Tell me the answer. Go to what? Tell me. 3 to 5 times 3 to the power 95. What's the answer?
3 power 98.
3 to 100.
No, 5 is in 95. So what's the answer?
3 to
3.
100.
3 to the power what? What's 5 plus 95?
100.
100. Right? Yeah, so this is the final answer. Okay, 3/5, 3 to the power 5 times 3 to the power 95, right? You what? You add the exponents, right? So 3, 5 plus 95, which is 100, right? Don't forget that, okay? This is called what? This is one of the laws of exponents, okay? Because we have to use them again in mathematics, right? You should not make any mistakes. Remember, this is wrong, this is right, this is wrong, okay? This is wrong. We don't have any formulas for these, but we have formulas for these, right? You got to remember how to handle the exponents, okay? How to handle the exponents. Because this is so useful, right? So useful. Now you can sketch, right? You can what? You can shift, right? Remember how to shift, right? You can shift up, shift down, right, left, right? That's easy, okay? That's standard, right? You can how to shift, okay? How to shift. Okay, so I think we can finish these. Okay, we can finish these easily, right? Easily. So let's go to next page. What's the next page? Let me check. These applications, I don't want to, these are just applications. I don't want to spend too much time on these. It just, okay, the number E, right? So the number E we have is a special number, right? So remember, for this special number, we have to remember this is okay, y to e2x, remember, right? Tell me what's the value for e, remember? We have done this in math definition. E is approximately equal to what? 2.7. Right, this is an irrational number, okay? So E is approximately equal to 2.71828, right? So E is between what? 2 and 3, right? Actually, E is larger than 1. Okay, so remember, okay, E is 2.7 something, right? Is what? Is greater than what? Than 1. Okay, E is between 2 and 3, right? So E is greater than 1. That's very important for you to know, okay? E is a real number greater than 1, okay? So therefore, the graph for this is what? Is increasing, right? Not decreasing, because E is larger than 1, right? It's increasing, okay? Increasing. Don't forget that, okay? E is about 2.7 something, right? You got to remember, okay? Now you can see the picture for E, right? See, this is 2x, right? So this is a picture for y equal to 3x, right? And now you can see the picture for e, okay? Now this is a picture for y equal to e2x, see? Right, y to e2x. E0 is always equal to 1, right? So this is, e is larger than 1, right? So the curve is what? Increasing, right? Increasing, okay? Increasing. And then this is the horizontal asymptote, right? This is the slope, right? So you got to remember, okay, how to handle this is, we give a name for this, right? For y to e2x, right? For y to e2x, it's called what? It's called, okay, it's a name for y to e2x. Okay, so it's called what? The natural exponential function. Whenever you see natural means what? Y equal to what? Y equal to e to x. Okay, y equal to e to x called what? The natural exponential function. Okay, whenever you see this word natural, it means what? The base is e. Okay, the base is e. Don't forget that. Okay, in the future, if I say, okay, I will have the so-called the natural exponential function, it's just y equal to e to x. Okay, e to x. E is a real number between 2 and 3, right? Especially e is larger than 1. E is 2.7, right? Something, right? Is larger than 1. Okay. So remember, okay, e is larger than 1. Okay, this is very important. So the graph is increasing, right? Tell me, this is even function or odd function for y to e to x? I will
Either.
ask you this question. You have just seen the picture for y to e to x, right? It's an increasing function. Now, this function is even function or odd function?
Neither.
Why? Why is it neither or neither? Why?
Because it can't be reflected across
Why
the
the
origin
function
or the
is even
y-axis.
not odd? Yes, very good, right? The function, the picture of this y to e to x is neither symmetrical with respect to y-axis nor symmetrical with respect to what? To the origin, right? So this function is neither even nor what? Nor odd, right? Because you got to remember, okay? But this function is increasing function, but neither even nor what? Nor odd, right? Very important for you to know, okay? Now, let me continue with the okay, with this, okay? Now look at this function. I want you to find its domain. What domain for this function? For natural expansion function, what domain? And what's the range for this function? By using interval notation, please find domain. And finally find the range for this function, y equal to e to x. What domain? Tell me, what domain? Please use interval notation to find domain. What domain? See it. Who want to volunteer
Negative
to have the answer?
infinity to infinity.
What? To? Yes, very good. You have to know how to write the answer, right? Negative infinity,
To infinity.
comma, right? Positive what? Infinity. Yes, that's the answer for domain. Now, how about for the range? Range is all the possible y values, right? Look at the picture. What?
I have a question for
What's
range.
the range here?
Since
Yes.
it never gonna hit the 0, it gonna be I forgot that symbol. It don't hit 0, so it's gonna be that symbol called.
No, you will not. If the y value will not hit 0, right? So what's the range? Open interval, right? 0
Yeah, that's what.
to what? Positive infinity.
Infinity.
Yeah, positive infinity, right? This 0 will not attain y because this is called what? Horizontal asymptote, right? So the y value will not attain 0, but will be very close to 0, right? So this open interval, okay? 0 to positive infinity. Don't forget that, okay? For the natural exponential function, the domain is from negative infinity to positive infinity. The range is from 0 to positive infinity. All right, it's very easy to see from the picture, right? You got to remember how to write down the domain and how to write down the range by using interval notation, right? This will be important for tomorrow's what? Quiz, right? So you got to learn how to find domain and how to find the range by using interval notations, all right? So got to learn something, right? Otherwise, you come here every day. If you don't learn something, then you just waste your time, right? Now we have finished these functions, okay? Finish these functions. Now you can sketch for these combinations, right? You know how to shift, right? How to shift, see? Right? How to shift, okay? This is a basic function. Then you know how to shift, right? How to switch, okay? So all these are very standard, okay? Let's go to the next page. What's that? Go to the next page. What's this? Exercises, okay? These just exercises. So this is nothing new here, just doing some example exercises, right? Now, this is the last section in chapter 1, okay? Called what? Inverse functions and logarithms, okay? So remember, log function is an inverse function to exponential function, right? So you got to remember that, okay? So not every function will have inverse, right? But for a certain function, it's called what? See, this function is called one function, right? For one function, it does have inverse, right? So here, there's a definition of so-called one-to-one function, okay? So please circle these, okay? Please circle these. One-to-one function. Okay, a function if it's called one-to-one means what? If it never takes on the same value twice, okay, that means that whenever x1 not equal to x2, the function values are not signed. Okay, this is a one-to-one function. Of course, not every function will be one-to-one, right? Now let me give you one example here. Okay, not every function will be one-to-one, right? Let's look at this function. Okay, this is 0, right? This is x, this is y. Okay, now this function is fx is equal to x squared, right? X squared. Okay, the picture is this, right? This is function fx equal to x squared. Question, is f11? Now question, is f 1-to-1? how to answer this question. Is fx equal to x squared, right? Is f 1 to 1? By using this definition. Right or wrong? The answer is no. Okay, answer is no. Okay, f is not 1 to 1. Why not 1 to 1? Why is this f is not 1 to 1? Because easy to see, right? -1 is not equal to 1, right? But f of -1 is equal to what? F1. They are both equal to what? Both equal to square, right? Equal to 1. That's why you can have a counter example, right? -1 not equal to 1, but the function value is same, right? And f -1 is -1 squared is 1. F1 is 1 squared is also equal to 1, right? So you have two distinct x values, but the y values are same, right? From picture is easy to see, right? Here you have 1, right? This is 1. This is -1, right? This is -1, right? They are not same, but the y value is the same. See, y value is same, right? Y value, they are both equal to 1, right? So therefore, the function is not 1, 1, right? Because for two different x values, you have same y value, right? Also, you can use what? So-called horizontal line test, right? If you draw the horizontal line, if it meets more than 1 point, then the function cannot be what? Cannot be 1, 1, right? So you can draw the horizontal line, right? You will meet 2 points here, right? So the function cannot be 1, 1. Okay. Now let's look at this function. Fx equal to x cubic power. The cubic function. Now everybody knows how to sketch these, right? How to sketch these. The graph for cubic function is easy to sketch, remember? Right? This is the graph, remember? Right? It's all the function, right? All the function. And passing through 0, 0, right? This is 0, 0, right? Now you can see that if we draw the horizontal line, right? It will meet only 1 point, right? It will meet only 1 point here, right? So this is what? This is a 1, 1 function. Okay, for fx equal to x cubed, indeed, it's a 1, 1 function, but fx equal to x squared is not 1, 1 function. Okay, so there are some functions which are 1, 1 function, but there are some functions which are not 1, 1, right? So remember, okay, x cubed is a 1 function, but x squared is not a 1 function. Okay, so for 1 function, we can find its inverse. But if it's not 1, 1, inverse does not exist. That's why people want to introduce 1 function. Okay, that's why. Okay, so you got to remember how to handle 1 function. Okay, 1 function. That's definition, right? Now look at this. Look at a picture of this. Is this a 1, 1 function or not? Is this a 1 function or not?
It's not.
This is
No.
right. Why it's not? William, why it's
Because-
not a 1, 1 function?
Because you draw
Because what?
because it hit more than
You draw a
one.
horizontal line, you meet how many points here? 2 points, right? This is x1, this is x2. They are not same, right? But the function values are same, right? So the function cannot be what? 1, 1.
1.
Okay, so remember, the function is not 1, 1, right? See, it's not 1, 1, right? Not 1, 1, not 1 to 1, right? Because x1 and x2 are distinct, but the function values are same, right? So the function is not what? 1 to 1 and not 1, 1. Okay, not 1, 1. So this is very important for you to understand when a function is 1, 1, one function is not 1, 1 by using what? By using the horizontal line test, right? If you know the picture, right? You can draw the horizontal line to test if it's 1, 1 or not, right? Okay, so the function cannot be 1, 1 because look at picture. it's very easy to see why not 1, 1, 1, right? These x1, x2 are not same, but the function values are same, right? So it cannot be 1, 1, okay? Cannot be 1. You want to see this video? Let's see it.
There's an easy way to determine whether a graph represents a one-to-one function in the xy plane, and that is the horizontal line test. If you can draw a horizontal line and it hits the graph in more than one spot, then it's not a one-to-one function. This is because a one-to-one function does not have more than one x value in the domain, which gives us a specific y value. Take a look at this graph, for example. Notice if we draw a horizontal line here, and we hit the graph more than once. So its graph cannot represent a one-to-one function. How about this graph? This is a one-to-one function. Notice no matter where you put the horizontal line, it will always intersect the graph at most once.
Look at this, okay?
Recall previously, we talked about the function which converts degrees Celsius to degrees Fahrenheit. F of c is equal to 9/5 c plus 32. Let us say now we want to convert degrees Fahrenheit to degrees Celsius. To do this, we need the inverse of this function. Notice f of c is equal to 9/5 c plus 32 is a one-to-one function. Since it's a linear function, so all we need to do is solve for c. First, subtract 32 from both sides, then multiply by the reciprocal of 9/5, which is 5/9, and we are left with c is equal to 5/9 times f minus 32, leading to c is equal to 5/9 f minus 32 times 5/9, giving us c is equal to 5/9 f minus 160 over 9. This is now the inverse of original function. C is now the dependent variable, and f is the independent variable.
Okay, right? This shows you how to find the inverse function. If the function is 1, 1, right? If the function is not 1, 1, the inverse function cannot exist, okay? Now, that's the meaning for this function is not 1, 1, right? Because look at that. Horizontal line test fails, right? Horizontal line fails. You got to know how to find the inverse, okay? Now, if f is 1, 1, you can find the inverse, right? So inverse function, the domain and the range are what? Are reversed, okay? So for y to fx, the domain and the range, okay, the inverse function, the domain is what? Is the range of the original function. And for the range of the inverse function is equal to the domain of the original function. Okay, so that's we have learned these, right? See, that's important for you to remember. Okay, so let me just circle these. Okay. Okay, f negative 1 means inverse. Okay, inverse. This is notation for inverse. Okay. The domain of f inverse equal to the range of f, right? And the range of f inverse function equal to domain of f. So these domain and range are what? Are switched for the inverse function, right? You got to remember this connection between inverse function and the original function, right? The domain of the inverse equal to the range of original function, and the range of the inverse equal to the domain of the original function, right? So of course, this f should be what? 1, 1. If f is not 1, 1, the inverse function does not exist, right? So of course, f should be 1, 1, right? Okay, so much for this. Okay, now this is the picture for, right? This is x to y, f. Now inverse means what? F inverse y go back to x, right? So let me draw a picture for you, right? See, x to y, right? This is f, okay? Y to fx. Now you go from y back to x, right? This is what? F inverse. Okay, it's very easy to understand, right? If f is 1, 1, okay, then fx equal to y, right? This f is original function. Now you have to what? You have to pull back y back to x. This becomes what? Inverse. Okay, so you got to understand how to define inverse, right? So y to fx, f is original function. If f is 1, 1, you can pull back, right? Then f inverse y to x. So let me write down, okay? So fx is equal to y, right? If f is 1, 1, then f inverse y, this is y, okay? Is equal to y, equal to x. Okay, look at the picture, right? Fx equal to y, and f inverse y equal to x. If f is 1, 1. If f is not 1, 1, 1, then this inverse does not exist, right? So remember, okay, this figure 5 is very nice for you to remember how to define inverse function, right? So this is very useful. You have to have a picture in mind, right? To understand what the inverse function means, right? What inverse function means. Okay, now you got to remember this is the, okay, I don't want this anymore. I want to clear all, okay, clear all. Okay. Now, the last one I think is the log function, right? Okay, don't forget that f inverse x does not mean 1 equal to 1 of fx, okay? They are not sign, okay? They are not sign. Now we have discussed the log function, right? So I don't want to spend a lot of time on log function. I think you have log function, right? You have log function, possibly in next page. Okay, next page. I think in next page. Yeah, next page for log function. So let me just remind you the definition of for log function, right? This is a last topic in this, okay, in this chapter, okay, log function. Now the definition, okay? So please remember how to define log function. Okay, this is the most important thing for you to remember, okay? Remember. Okay, y equal to log bx, as I said yesterday, how to define the log function, if only if what? X equal to b to the power y. Okay, so you can switch from exponential function to log function. Also, you can go from log function to exponential function, right? So remember, log function and exponential functions are inverse functions to each other. Okay, now this definition you got to remember. Okay, you got to remember. Log bx equal to y if only if x equal to b to the power y. Okay, this is the most important definition in this section. Okay, how to define the log function, right? That's definition. Okay, definition. You got to remember. Okay, now this is the this is the picture for log. Okay. This is y equal to log bx if b larger than 1. Okay, this is the picture. And I told you yesterday, right? The picture, right? Now for b less than 1, the picture is, I think, is this. Okay, this will always be larger than 1, right? For b smaller than 1, the picture will be slightly different, will be decreasing. Now this is what? This is law of the logarithms. You got to remember these laws. Okay, these laws are so important. So let me. Okay. Okay, you have. Can you see it? Okay, I don't know how to. Okay, hold on. Yeah, and okay, do it again. Okay. Okay, so this is laws of what? Laws of logarithms. We learned the laws of exponents, right? So in this section, we got to remember the laws of logarithms, right? And actually we have learned this before, right? So refresh your memory, okay? Log bxy equal to log bx plus log by. Log bx over y is log bx minus log by. And log bx to r, you can put r outside, right? So it's r log bx, okay? R is any real number, right? So you have lots of exponents, right? And in this section, you have lots of what? Logarithms, right? All this is standard. We have learned them before, right? So you have lots of logarithms, okay? So we have finished this section, okay? Right, so we have learned a lot of things in this chapter. Actually, this is just review, right? Just review. Now, the last thing is that for natural logarithms, right, we use this notation, okay? The base is e, right? We use this notation. Don't forget that, okay? We use this notation. Ln, n means natural, right? L means log, right? So natural logarithms is Ln. Ln means what? The base is e, okay? The base is e. So the notation for natural logarithms, okay? Natural logarithm. This is lnx is log ex. The notation for natural log, okay? So much for today. The time is over, right? Time is over. Any questions so far? So we have finished the review for chapter 1, okay? So starting on Thursday, we will go to chapter 2, okay? Because tomorrow will be the quiz session, right? Will be the dissertation, right? So on Thursday, we will start with chapter 2, okay? Chapter 2. So chapter 1, review.